2, 1. Okay, so hello everyone. This is problem session 9 of the homotopy type theory track of the HoTTEST Summer School 2022. So as usual, we'll be simply going through the worksheet, and I'll try to sort of unfold all the solutions that are already posted. So they're absolutely valid. What we're doing here is to sort of try to make them less informal, maybe more intuitive, maybe unblack box some of the constructions happening. So with that said, I'll be going forward. They're supposed to be, so there are only 4 problems here, and they're not too wordy, so we'll not be sticking around for long, but hopefully this will still be informative. So let's start with the problem regarding coproducts. Problem 1. And as usual, if my handwriting is a little bit messy, or you have any comments whatsoever, please drop them in the chat or unmute yourself. Okay. So problem 1 asks you to show. So part A, show that we have an equivalence of the coproduct of A and B going to C with a product of A going into C times B going into C. So for those of you who are familiar with category theory, this is sort of the usual property of coproducts. So mapping out of them is determined exactly by mapping out of each individual contact, of each individual part of the coproduct. However, this also makes sense, I think, kind of said theoretically. If you think about types as just things with terms in them, then and the coproduct as sort of just combining the two in 2 different layers of the type, then sort of how do you map out of it? Well, to map out of something, you need an assignment on each of these sections of these terms. So you just create an assignment on one part and on another. So actually, we'll not be showing this straightforwardly, in a sense that I'll be making it in a little bit of a different fashion that it is done in the solution. So proof. This is simply a consequence of the dependent case. What I mean by that, is that since we have universes, we can get constant type families. So if, for example, C is non-dependent, then you can simply postulate C as this constant function that takes around, that goes from whatever context you have and sort of maps it into the universe. And so this constant thing on every assignment will just give you your type C, which you can form independently of A and B. Hence, you will be able to get an an equivalent statement. So this function is gonna give you something which is equivalent to your original sort of standard type. So instead, we'll be going into the dependent case. So show that. So, and what's the dependent case? Well, we just sort of pi everything. So here we have pi x a plus b and cx. So here I'm not, everything, we assume everything is such that everything type checks. So A is a type, B is a type, so A plus B is a type, etc. So it should be evident from context, which we're assuming here, is equivalent to a product of pi x and a of cx and pi x and b of cx. Yep. Okay. So here will be basically, what do we need? Proof. What do we need? So we need a function first. Well, we need an equivalence, and equivalence is established. The data are two functions going back and forth, and the relevant homotopies. So I mean, there are two functions in the sense that when we assume functional extensionality, there's only going to be two. But remember to make sure that the property of being equivalent is actually a property. You have to do this double sigmas. So, okay, what do we need? First, we need a function that goes from here to here. Okay, so let f be this dependent function here, x. Okay, so we specify an element of the codomain as follows. So first things first, we specify component-wise and then apply the pair constructor to get an element of the product. So first we need, we define, so let's say that this function is going to be termed f. And so f, I'm going to say it. So first we define a function f1. It's going to be in here by, so on the input x, we need some element of cx. So instead we define it to be our original f, right, as we have here, applied to the constructor in left of x, and this is going to give us an element of cx, and so we're done. Okay. On the second component, of course, is going to be similar. So x is in b, is dependent by f2 at x. It's going to be defined as original f applied to the right inclusion of x. Okay. So, and this gives us our assignment. Okay. So let's specify now our second part of an equivalence. So here we need to go from, well, let me write this explicitly. Then f at f is going to be defined as just applying the pair constructor to these two functions. Okay. Any questions thus far? Okay. So right, the second part is to get now a function from product. Okay. To the shift in dependency. So actually, no, there's, when you're going to be doing this in Agda, for example, there's a bit of a trick in terms of shifting of dependencies. So originally, C is a dependent type, which depends on the coproduct, and you can shift those dependencies to individual ones. But you have to be a bit careful regarding that, and try figuring out what's actually happening. It's a good sort of extra exercise outside of this. Okay, so I mean, it's basically written in the solution. What you basically need to do is I don't want to keep this black boxed as well. So let's instead write this inland X. And this is C in right X. So basically C is a dependent type, which is dependent specifically on the coproduct. So it's not really by itself dependent on either A or B. However, as long as you apply the constructors, you make that dependency evident, if that makes sense. Then you can actually, it's actually dependent on the elements of the coproduct, and applying the constructors, you actually get this dependency. Okay. So let me just change this everywhere. X. And here to in right X. Here also in left X. And here to in right X. Okay. So let's specify the second function. So let X, well, it's not overused, but let's Y be n be of the said product type. Induct on Y to get Y as F1 and F2 of the required types. So right, so we now see them as a pair. Now define G at F1, F2 as a function, which sort of well, let's do this exactly. Define G F1, F2 as a function F such that, how do we define it? Well, F at some variable Z, we want to define, so induct on Z So f here is supposed to be of the type of this dependent function space, which is where C is dependent on the coproduct. So we induct on Z as an element of the coproduct. So first case is if it's inland A for A, then F land A is, of course, F1 at A. Yeah. And in the second case, where Z is in right of B for in B, F in right B is going to be F2 at B. All right, so F1 is going to be a function from F1 is here going to be a function of this type, and F2 is going to be a function of this type. Okay, so everything should be able to type check. So all is clear? Okay. So the second part is, well, the third part now is to provide, we provide homotopes. So first, we, what do we want to have? We have F and then G, and we want to be topic to the identity map at what? So G goes to the to this dependent function space, Cx. Okay, so take F in this function space, Cx. So what we want to show is that applying to this is going to be equal to F. So here, I mean, in the solution, there's a lot going on with regards to definitional equalities, and it's sort of always tricky to figure out when definitional equalities really work, because sometimes in your head, you're assuming some more complicated rules for your type former, such as the eta rules, which provide you that sort of every element is going to be every element of some dependent function type is going to be sort of canonically represented by constructor. However, we don't want to do that, and we, you know, sometimes it's better not to do that because it gives you sort of allows you more models, maybe. However, we don't really need to do that. So we're assuming functional extensionality. So in some way, if you feel like definitionally something isn't working out on paper, if you don't have a theorem prover at hand, and you may not know what exact what exact rules are assumed in the complicated type formers that you have, you just use functional extensionality. So here, both of those are functions. You can use functional extensionality. So what it is to see equality pointwise, right? So basically what we really need is a homotopy between those two functions. So let Z be an element of the coproduct and induct. So we have G, F at F apply to, for example, in left A, where A for A in A, we get then this sort of general meta arrow. So let's look at the definition. Oh, I should be careful with writing F's, small ones and big ones. So how do we define F? So, okay, F takes this function and it gives you this product of F1 and F2, where those is defined by F. So here we apply G to this, And so what does G do? G also defines them pointwise, right? So it's going to be actually F1 at A is going to be the same as F as in left A. Okay. Does everything type check? Everything makes sense? Yeah. Okay, nice. Yeah. I mean, doing this on paper, there's always a problem that maybe, we're much worse than machines at checking this sort of stuff. So, okay. So, and I'm going to say it's similar for the case in B, in right B, right? So it's going to be basically the same computation. Okay. So the last part of the puzzle, it's sort of a different direction. So it's now going to be G applied to, so G and then F, and we need a homotopy with this dependent function space. So this is going to be C in X times pi B in right. Hopefully you also understand that sort of, for example, usually theorem provers don't really like using the same variables as I do. So hopefully you understand that it's sort of these would be different when you usually formalize. They need to be fresh usually when you introduce new dependencies, but hopefully that's understandable. Okay, so let F be of the product type, induct to get F as this product F1 and F2, which they're of appropriate types. So now what we want is FG at F1, F2 is equal to F1, F2. Okay. And again, looking at definitions of FG, so these agree pairwise. So what I mean is the first projection of FG and F1, F2 is going to be the same as F1, and the second projection FG, F1, F2 is going to be the same as F2, using, again, functional extensionality. So check them pointwise. So you can certainly do that. But this is sort of just unwrapping definitions again. So everything should be clear. So okay, so with this, we are done. This indeed establishes an equivalence. Okay, so here we sort of just unraveled a bit of the very type theoretic notation that is being introduced in the solution to the worksheet. Any questions? Okay, so let's move on then to the second problem. Okay, problem 2. So okay, it sort of has two parts. So first is the way that I'm going to split it is by noticing the sort of contractibility the question of being contractible is a question of first being inhabited and the second of being a proposition. So what I'm going to do is to prove that the case for contractibility, and then note that the proof that we used in the last part is actually going to be relying solely on the fact that B of X is a proposition for all X and A. Okay, so let me make it clear what I mean here. So, okay, so let there be some sort of a witness that for all X and A, we have a witness that Bx is contractible. Okay, good. So claim we have that general type here, if X is contractible. So sort of point-wise contractibility implies that the entire dependent function space is going to be contractible. Okay, so what's the proof? Well, what is contractibility? Again, it's inhabitedness plus propositionality. So first need a center of contraction. Yet we have what? So we have a function which sort of takes, yet we have, so let me better say that, define the center in the space by, so C at X is going to be defined by projecting the second component at F at X. So remember, so that is contractible stands for this exists Y in Bx, such that for all, oh, this should be the first. Yeah, for all Z in Bx, Y is equal to Z. Okay, so simply take the element of that sigma type and get this first witness. So this sort of sigma usually, right, corresponds informally to existence claims. So that's our actual witness. Okay, so good. Now we need to prove that the type is a proposition. So take G1, G2 in our dependent function space, Bx. Want to show that these two are going to be equal. Okay, so we use function extensionality again to check pointwise. So let X be an A, and so check. Let's say it like this. Question is J1 at X equal to J2 at X? And the answer is yes, as B of X is contractible. In particular, a proposition. So all of its elements are going to have some inhabited, all of its elements are going to have an inhabited identity type. So in particular, what can do sort of in type theoretic terms, you apply F, which is our original sort of element of this, F. Yeah, I don't want to do that currently, but hopefully you understand how to get that. So contractibility implies propositionness, and as long as you have this proof of being a proposition, then you get all of your results. Okay. So, and the second part is show that if for all X and A is prop, Bx, then the entire function space is a proposition. And the proof is sort of like, so now we don't need to have a witness. Now we just need to show that our entire function space is a proposition. Yet note that here, our proof of the fact that the entire function space is a proposition relied well on functional extensionality, which we always assume. But moreover, it just relies on the fact that Bx is a proposition for all X and A. So proof can be extracted from previous one, right? So of course, it's not going to be as straightforward as sort of, maybe you can do something to actually type theoretically sort of get out of this proof, the proof about propositions. But informally, the proof of the second fact sort of underlies what we have in the first one. Let me put it in parentheses. The prop part relied only on the fact that we have a witness to this. Okay, good. And we're done with question 2. Any questions at this point?
Yes, maybe a naive question, but I would like to ask, sorry if it is a naive question, but is B of X being contractible a fundamental requirement for having G1 equals G2 in the previous? I mean, we are defining G1 and G2 as being, we have provided the same definition for both. So I asked myself if in order to prove G1 of X equals G2 of X, it is required B of X being contractible.
So no, we don't need that. So recall being a proposition is equivalent, being a proposition, let's say A, which is a type, well, this is maybe confusing. C, being a proposition, is equivalent to having a witness to, for all X and Y and C, X equals Y, right? So basically, we can identify everything. The only difference with contractibility is that in contractibility, we actually have a witness to this. So another way of looking at propositions are like either come as unit type or empty, or and contractible types just come as units. So here, what we needed to show is that by functional extensionality is that they're pointwise equal. In particular, these two are elements of B of X. But well, let me write it this way. This identification is happening in B of X, yeah. And so we aren't asking that they're both equal to a specific point that we already have. This is a stronger requirement. What we're asking is for just a witness that they're equal, which is provided by a fact that it's a proposition. We don't even need contractibility for this.
Okay.
So
okay.
we needed contractibility only to find this, only to find an actual center of contraction.
Okay.
Without that, we would not be able to find a center.
Okay. Okay. Thank you.
Okay, for sure. Okay. So let's move into question 3. Problem 3. Okay. So claim. So let's say let A be a type. Then is contractible. A is a proposition. Again, as usual, it's good to want to have a yes or no answer to certain questions. So the fact that we are forming these types using words is and contractible, we want to actually have a yes or no answer. Is it contractible or not? So it's good to actually have that these properties of being truncated are actual properties in a type theoretic language. Okay, so proof. So we're going to sort of unfold the definition of being contractible. Just once again, let X and Y be elements of this type. Let's say Z1 in A for all Z2 in A, X equals Y. Yeah. So want to show, our goal is to show that X is going to be equal to Y. Okay. So induct on X, Y, so that, they're elements of the sigma type, so there are going to be some dependent pairs. So first one is going to be like A1, F1, and Y is going to be A2, F2. Okay, good. So now note that A1 equals A2 as A is contractible. In particular, again, it is a proposition. Okay, so we do have a witness, let's say P, that these two are equal by characterization of identity in sigma types suffices to show that, what do we need? Well, we need sort of to transport one of the elements of the second one, of the second part of the dependent pair using P, and then show the needed equality. So we transport P F1 and ask if it's still equal to F2. Okay. So these are, so this is all happening equals to F2, yeah? So where is this all happening? This is happening in the function space of Z2 and A, and A2 is equal to Z2, yeah? So note, what do we have? A is contractible. One second. Is contractible. So a proposition. So we have a witness to is contractible. A2 equals Z2. Now, by problem I should say for, let me write it this way, this Z2 in A. Okay. Now, by problem 2, right? So by problem 2, we have that the entire function space, yeah, is contractible. So in particular, any of its, elements are going to be equal. We're going to have a witness to that. So particular, the transported version of F1 is going to be equal to F2. Okay, so that's that. It's sort of very abstract and it sort of pops out of nowhere. But this is it. And this is a very nice proof that sort of relies on the one we did in the previous problem. Any questions at this point? Okay. And from this is sort of our base case of actually showing something that I've mentioned before, and in particular that we want to have that the property of being truncated is actually a property. So part B is we claim that for K in T, where T is sort of encoding our truncation levels from -2 and up, and a type, we have that is truncated A is a property. So it's a yes or no answer. Okay, so proof. So here it might be actually tricky when you want to formalize this in a theorem prover. You might want to really put K before assuming A is a type so that the induction will go smoothly. So, but the proof is, induct on K. So when K is going to be -2, use part A, so that we already to get a witness to is prop is contra A. Okay. So for the inductive step, let K be some n+1 and assume we have some, I don't know, f of is truncated the kth level of A for all A in some type universe. Okay. Okay. So want to show by definition of is truncated K+1 that for all x, y in A have that the identity type is K truncated. Yep. Yet x equals y is a type, sort of a very evident conclusion. So using the inductive hypothesis, so f applied to x equals y, we are done. Okay, so this was maybe a little bit elegant, but this is what I've this is regarding what I mentioned about being careful about where you actually proceed with induction. Maybe some type systems don't really, some theorem provers don't really like this sort of messing things left and right, but basically our induction hypothesis is right that any appropriate type is going to be K truncated as being a property. Oh, wait, what was I trying to say? I should say that we assume that F is, so we take this and we want to say that it's a property. Yeah? Yes. So, and we want to show by definition that, yes, that for all x, y, this is prop. Okay. So yes, all is good now, I think. Let me know if you've noted any other things I missed about. This should be it. So basically the induction hypothesis here, relying on this sort of A belonging to some specific universe, lets us actually do this induction smoothly by the simple fact that the identity type is indeed a type. Okay. All right. So I guess if there are no questions. Okay, yeah. So I'd recommend you do this actually in a theorem prover, just to make sure there's like this subtle substitution going on. Sometimes it's not really evident where the induction is happening. So I urge you to try and formalize this actually in that. 3A. Okay. So where what's the actual problem in formalizing 3A? Where do you hit the wall? With a path over. I'm not sure. I'm suddenly not as familiar with the Agda notation and the library that you use. So can you sort of informally explain what's actually happening there? Uh-huh. Okay, so what are we trying to say here? Okay, so maybe X to Y to okay. Yeah, I mean, so this part is established by the second problem, right? So as long as you formalize the second problem, you should know that after transporting, you're going to get an equality happening there from contractibility. So is the problem that you haven't yet formalized the characterization of equality in sigma types? Yeah. I'm not sure exactly how I can help you right now. Maybe you can message me in Discord. Oh yeah. So here you really need to use the contractibility argument or proposition argument, so that this is actually So in case you would be interested, you can just message me on Discord, and I'll be able to answer your questions outside of the process. Okay, so let's then quickly finish with the sort of the final fourth problem. So problem, oh, I'm sorry. Okay, so problem 4, sorry for that. So there's this entire a very good discussion about why we want to have a type is equivalent to be a proposition. And generally, we have now a new notion of what it means to sort of be equivalent. So consider, so for all y and b, a type is contractible. fiber of f at y. Okay, where so let's just unfold what this means. It is contra sigma. Well, let me instead maybe provide you with a picture. So sort of the question is, why is contractibility of fiber supposed to be a good stand-in for being equivalent? So sort of intuition, the intuition is that of sets. So how do you usually identify sets? Usually the way you identify sets is by using bijections. So sort of think about there being some type at the bottom, some type at the top, have this function f going on. So first, contractibility of the fiber is the question of existence. So what this means is that if you have this fiber y, there's actually something being mapped to it. And then afterwards, what you're saying, let me maybe show it in a bigger way, that actually whatever is mapped to, there are going to be paths in between everything, etc. So in other words, inhabitedness sort of informally corresponds to surjectivity, and actual sort of the proposition part, positionality corresponds to the injectivity part, sort of that you're actually identifying the fiber. And so that sort of intuitively gets you a bijection. Of course, it's a sort of it's an intuitive explanation, I guess, if you're more familiar with sets and unstructured objects. It's not very precise, but this is something that might get you going. So we want to show that actually this type fiber f at y is a proposition. So, but actually, note is contractible fiber of f at y is a proposition. The claim that something is contractible for any type is going to be a proposition by problem 3a. Moreover, by problem 2, as sort of pointwise, this dependent type is going to be a proposition, that so is this. So y is a prop. And we are done. So actually, why does this intuition work? And with that, I urge you to rewatch lecture 6, which proves that every contractible fiber-wise map is an equivalence, and every equivalence gives rise to a map with contractible fibers. Okay, so that you've already proven this, you just didn't realize maybe how important it is to have these different notions of what it means to be contractible. Why is it important? Well, you really want the being equivalent to be a property, and the property of a map being an equivalence to be a property. However, different characterizations of this property may give you more data to work with. So maybe it gives you several functions, maybe it gives you even more equalities than needed. And that is something that you have to consider. It's good to have more characterizations of being equivalent. Sometimes that really helps. And with that, we are done with today's session, and I'm gonna stop the recording. Thank you so much for attending.